In the previous video, we were discussing about the unit of work. The unit of work done in SI system is Joule. Joule is the unit of work done in SI system, and in CGS system of unit, the unit of work is erg. Erg is the CGS unit of work done, and their relation between joule and erg. So 1 joule equals to 10 raised to the power 7 erg, which we have seen in our previous video. Now we talk about gravitational unit of work. Gravitational unit of work. In SI system, the gravitational unit of work is kilogram meter. In SI system, gravitational unit of work is kilogram meter. In SI system, the gravitational unit of work is kilogram meter, and 1 kilogram meter of a work, 1 kilogram meter of a work is said to be done the gravitational unit of work is kilogram meter. Now the definition of 1 kilogram meter. So 1 kilogram meter of a work is said to be done when a force of 1 kilogram weight, when a force of 1 kilogram weight So 1 kilogram meter of a work is said to be done when a force of 1 kilogram weight displaces a body through 1 meter in its own direction. So this is the definition of 1 kilogram meter of work. 1 kilogram meter of work is said to be done when a force of 1 kilogram weight, kg weight is the unit of force. So when a force of 1 kilogram weight displaces a body through 1 meter, when a force of 1 kilogram weight displaces a body through 1 meter in its own direction. So this is the definition of 1 kilogram meter of a work, and the gravitational unit of work is kilogram meter. So 1 kilogram meter, 1 kg meter, 1 kilogram meter work is equals to 1 kilogram weight into displaces a body through 1 meter. So 1 kilogram weight equals to 1 kilogram meter work done is equals to 1 kilogram weight into 1 meter, and 1 kg weight is equals to 9.8 Newton. 1 kg weight is equals to 9.8 Newton. So 9.8 Newton into 1 meter. And we know that Newton into meter is the unit of work. Newton into meter. So 9.8 into 1, 9.8 Newton meter. And Newton meter is called joule. So 1 kg meter work is equals to 9.8 joule. 1 kilogram meter work is equals to 9.8 joule. So the gravitational unit of work is kg meter, kilogram meter, and this is the definition of kilogram meter. 1 kilogram meter of a work is said to be done when a force of 1 kilogram weight displaces a body through 1 meter. So 1 kilogram meter work is equals to 1 kg weight force into displacement, and 1 kg weight is equals to 9.8 Newton. So 9.8 Newton into 1 meter means 9.8 Newton meter, and Newton meter is called joule. And 1 gram centimeter work, convert kg into gram. So 1 gram centimeter work is equals to 980 erg. In CGS system, we convert kg into gram and meter into centimeter. So 1 gram centimeter gravitational work is equals to 980 erg. So this is in SI system or MK system, and this unit 1 gram centimeter is in CGS system of unit. In CGS system of unit. Now we talk about work done in terms of rectangular component. Work done in terms of rectangular component. Work done in terms of rectangular component. So we know the formula for work done. Work done equals to force into displacement. Let the component of force in 3 dimensions F is given by Fx I cap. The component of force F is given by Fx I cap plus Fy j cap and plus Fz k cap. So these are the component of force in along x axis, along y axis and along z axis. Similarly, the component of the displacement S is given by Sx I cap plus Sy j cap plus Sz k cap. Displacement along x axis, y axis and z axis. Now work done is given by dot product of force vector and displacement vector. So put the value of F and S. So Fx I cap plus Fy j cap plus Fz k cap dot Sx I cap plus Sy j cap plus Sz k cap. Now we do the dot product. So Fx I dot I 1. So Fx into Sx plus Fy into Sy and J dot J is 1. So Fy Sy plus Fz Sz and K dot K 1. So plus Fz into Sz. So this is the work done in terms of rectangular component. W equals to Fx into Sx plus Fy into Sy plus Fz into Sj. So the rectangular components of work or work done in terms of a rectangular component. Now the next topic, work done by a variable force. Work done by a variable force. Work done by a variable force. This is x-axis and along x-axis there is displacement and along y-axis there is a force F and a variable force acting in a direction of x-axis. A variable force acts in the direction of x-axis. At every point of this graph, the value of force gets changed. So this is the variable force acting along the x direction. We divide this force into various small segments. This is the initial position xi and final position xf, xi and xf. Initial position and this is the final position, and at every point the value of the magnitude of the force is different. So suppose a variable force acts on a particle in x direction. Let a variable force acts on a particle in x direction. There is a variable force x acts in a particle, acts on a particle in x direction. We have to calculate the work done when the body moves from initial position xi to the final position xn. To calculate the work done, when particle moves from initial position xi when a particle moves from initial position xi to the final position xf. There is a variable force acts in a particle in x direction, and due to the variable applied force, particle displaces from the position xi to xf, and we have to calculate the work done when a particle goes from initial position xi to the final position xf under the action of force. So we divide the displacement into a large number of a small displacement. We divide the whole displacement in a large number of a small displacement delta x, and let A, B, C, D, and this each displacement is delta x. Each width of the displacement is delta x, and one of the width we have taken, and we divide the whole displacement into large number of equal displacements delta x. So during a small displacement delta x, the force assumed to be constant. During a small displacement delta x, the force assumed to be constant. Let the force is constant during let the force is constant during a small displacement delta x. We divided the whole displacement from initial position to the final position. We divided the whole displacement in equal intervals, and the equal intervals are delta x. Each equal intervals are delta x, and we assume that in a interval delta x, in a particular interval delta x, the force acts on a particle is constant. So the work done W equals to work done W equals to F into delta x. F into delta x, force into displacement. Force into displacement, F into delta x, and F is a constant force. Let the force is constant during the small displacement delta x. Let the force F is constant. We assume that in this interval the force is constant. So work done W equals to force into displacement, which is also equals to area of rectangle, area of rectangle ABC. So the work done by the variable force is found by finding the area of a rectangle and adding areas of all rectangles, we get the total work done. This is the work done equals to area of ABCD. Similarly, when we add all these areas, when we add all the area of rectangle, we get the total work done from initial position xi to final position fxf. So adding areas of all rectangles, adding areas of all rectangles, we get the total work done. We get the total work done. Adding the areas of all rectangles, we get the total work done, and total work done is written as W equals to summation sigma. Sigma means we are adding all these small areas, and lower limit from xi to xf and f into delta x. So W equals to sigma xi to xf f into delta x. And for delta x tends to 0, we can convert this work done in terms of integration. So W equals to integration lower limit xi to upper limit xf and f into delta x. So we use the definite integration for finding the work done by a variable force. If we have to find the work done by the variable force, then we use the concept of integration. W equals to integration lower limit xi to upper limit xf and force into displacement f into ds. So this is the way to find the work done by a variable force. A variable force acts on a particle and particle displaces from initial position xi to xf. Then work done, we divide the whole displacement into a large number of large number of rectangles, and among all these rectangles we suppose we consider one of the rectangle whose width is delta x and the force acting is F. So work done equals to force into displacement F into delta x, which is also equals to area of rectangle ABCD. And when we add the areas of all these rectangles, we get the total work done in displacing a body from xi to xf. And total work done is given by summation or sigma. This is the sign of sigma. Xi to xf, lower limit and upper limit, f into dx delta x, and which has been also written in terms of integration. Total work done equals to integration xi to xf, lower limit, upper limit, and f into delta x. So in the next video, we discuss the numericals based on the theory of work done.